Welcome to Advanced Data Analysis 1 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, I'll help get you started with Class 8, an Introduction to Linear Regression. All right, so we're going to download the QMD file, save link as, and I'll put that into the folder where I do our class analyses. Let's take a look at the HTML as well, just to have a sense of what's here. Looks like there's 10 questions to answer, roughly. And we're going to read some data in, look at residuals from a regression model, look at the relationship and predictions, and evaluate some model diagnostics. All right. This assignment comes from the Open Intro Labs site. It's lab number 8 on simple linear regression. So there is a lot of detail there at the website, and we will open that link to review the questions as we go. And can't get rid of the menu. Hopefully that's big enough for most of you to read on your screens. We'll go over to RStudio, and we will open from the path assignment 8. There it is. And as always, when you first open a file, set the working directory to the source file location. And that changes the path that appears just above the console window, and then render it. If there's any data or output, it will read and write from that directory. Okay, it's got 21 code chunks. I will open up that HTML. Okay. So this is our current HTML. It is exactly the same as what's on the website. So let's go over to the assignment and review what's there. All right, so we're going to look at data from the Human Freedom Index. It's a report, and in particular the data set sorry, the data set is from those reports, and we'll be summarizing some relationships. All right, there are some packages that we need. This stats R package is only used for a like a little demonstration where you are guessing at where the line is. So you might do an install packages if that doesn't run on your computer. This broom, I think, is a package that we probably installed, but if you get an error when you try to render it about the package name not being available, do an install.packages for these two packages. All right. We do not need to worry about a lab report. And each question or each exercise here is one of the questions in our report. Okay, so this here, number 1, data basics. I gave it a title, data basics. These are the two questions. What are the dimensions of the data set? And what does each row represent? All right, so we're going to start looking at this data set. We're working with the Open Intro Package datasets HFI for the Human Freedom Index. And let's just jump into it. Let's take a look at that data set. So we'll go over to RStudio. I'll do my coding up here in the editor window, and then we'll run the code down in the console. Okay. So this data set HFI is from the package Open Intro. If you do a data command on that, it loads the package. So in our environment, I should have shown you before. Yeah, let's sweep the environment. This little broom up here is one way to delete all the objects in your environment, and I always include hidden objects. I don't know what they are, but I don't want them around. So we're going to run that data command, and now we've got this HFI. It actually tells you right here what the dimensions are. If you look at the structure of this data, well, let's start more simply. The dimension, DIM, of the data set will give you the number of rows and columns. So that's part of the answer, right? The dimensions. And what does each row represent? Well, we'll need to look at the data set to understand what it looks like. If we print it, let me scroll up, just with HFI, we can start to get an idea here. We've got year, an ISO code, okay, but then we've got countries and region. So within each country, there's a specific region. I guess, you know what, I think it's actually countries within regions, right? We don't have any, oh yeah, we've got, here's Central Asia, Armenia, and so we've got multiple countries there. So within a region, there's a different country, and each country has an ISO code. Okay, and we have years for each one. We have a bunch of variables that follow, 123 variables total. And you can see that there are some missing values for years. But it looks like every row is some set of values associated with the Human Freedom Index report, where each row is a country and a year. Okay, and so presumably we're going to follow different countries over time. Let's choose just this first country, Albania, and see what we've got there for that country, right? So if we take HFI and we select, how about filter? Right, filter is a way of selecting rows. Filter where country, right? Countries double equals the name Albania. Press enter. Oh, rats. Let's go up and find the name again. Looks like countries all lowercase. Oh, you know what? We haven't loaded our R packages. So we skipped over the first code chunk, and we didn't have the appropriate packages. So let's take a look at HFI now. You can see it actually displays different because the structure is actually a tibble, which is the data format that tidyverse supports. Okay, and now if we try this filter command, we will get, for Albania, years 2008 up to 2006. That's 9 rows, and that's all of them. Okay, so it has 9 years worth of information. And then you can start to see how things change over time, right? Okay, so I'm comfortable with what each row represents. Very good. I will, just for the sake of it, put this piece of code up here and comment it. It's something that I used for data exploration. It helped me learn something. It's nice to have a record of it. All right. I'm not going to type in the answers. I'm just going to talk them through. You can get from this video what you'll get from it. All right. All right, the next question, let me just go back to the website and double check. Here we've got 3 rapid fire exercises, all just looking at this data set. Okay. So we're not missing any additional context is the point. The data set spans lots of years, but we're only interested in data from 2016. Okay, so actually, hey, we started doing something up here with this data set. It says, filter the data HFI, data frame for year 2016. Is that an original typo? Or is that one that I put in there? I'm not sure. Probably I put that in. Select the listed variables. So they actually say select the 6 variables, but they never say what the 6 variables are. Anyway, I'm giving you these variables to select. And assign the result to this data frame, HFI underscore 2016. Okay, so the word filter is going to be used to select rows, and the word select is to select columns. Okay, so filter subsets rows, select subsets columns. And you can do this in either order. Let's do it in the order that it asked us for. So we can do year where the year double equals 2016, okay? And then select these variables. Well, someone was nice enough to type them for us, so we don't need to type them again. We don't need any of those left ticks surrounding the text. Let's see if we can do a find and replace. So if we select this, I'm going to do Control F, but I'll show you. You can do Edit. There must be Find somewhere. Yeah, Find. Okay, so we're going to select the left tick mark, and we're going to replace that with nothing. And you can see the first one's already selected. Okay, and then we're going to do Next. Oh no, we're going to do Replace, and we can just click through, and that will remove each of them. Okay, and it did say in selections, so I could have just said all. I was worried about it wrapping and finding other tick marks, but in selection was selected. We also don't need these stars, but we do need commas to separate the fields. All right, so that looks like I'm going to start with the data set. I'm going to choose these rows wherever the year is 2016. Sorry. And then I'm going to select the columns, these specific columns. So let's run this piece of code. And HFI 2016, if we just print it, we see, we can give ourselves a little more space, 126 rows. That refers to the 126 countries in this data set and the 7 variables that we asked for. Excellent. We've got what we need. If you wanted to print the whole thing, see down here it says print n equals to see more rows. I'll show you two things. You can do print n equals infinity. We'll print all of them. Okay, and then you can also, sometimes you don't see all the columns, and so you can also do width equals infinity, and that will show you all the columns. So that guarantees that you'll see everything up to the limit that R prints, which I think is 1,000 or 2,000 or 10,000 rows. I forget what the default is because I've increased mine. Anyway, so there's the full data set. And United States is in there. Okay. Very good. Model. Okay, number 3, linear regression. What type of plot would you use to display the relationship between personal freedom score, that's PF score, and PF expression control? Presumably that's personal freedom expression control. Plot this relationship using the variable PF expression control as the predictor. The predictor is the X variable, and the response is the Y variable. All right, so we need to create a plot. I always get started with a plot by finding code to do that. And I always find code from my class. So if I go to the course website and scroll up to this example homework document, this is from a previous year, but if I look at the HTML document and we want a scatter plot. I don't know if okay, here we go. Okay, right, yeah, that's a good way to actually navigate this document. So if you scroll down through the table of contents at the top, data management is number 3, number 4 is graphing and tabulating, graphing numeric variables, okay, bivariate graphs, scatter plot for regression. So we got 2 numeric variables, that's the one we want. I'm going to click there, we'll jump down, and this will get me started. Okay, this is a terrible data set for scatterplot, but this is great code for a scatterplot. So let's grab that, bring it over here. We don't need this ggplot library thing here there. Okay, we just need to fill in the data set and the X and Y variables. So the data set was HFI 2016. I remembered it by looking up here in the environment window. The X variable is PF expression control. The Y variable is the PF score. It's going to plot points. Alpha is how much opacity there is. That's the inverse of transparency. It takes 4 points here, if a quarter, it takes 4 points to lay on top of each other to be completely opaque. Think of like stained glass or something. Let's just make that a half for now. That's only really important if there's lots of points and there's lots of points laying on top of each other. And I'm going to take the rest of this away and just create a scatter plot with points. Okay, so that is the beginning plot. We've got our x and y variable. Looks like there's a nice positive relationship here. We can add a smoother, and it's going to put a regression line on there. Okay, and another thing that is sometimes interesting to do if you're not quite sure if the curve or if the data is straight line relationship or not, is you can add a default smoother, but I'm going to change the color to red. How about line type equals dashed and no standard error? So if I run that, you can see a red dashed line, and that red dashed line basically follows that blue straight line. So that says to me that the smoothing curve that's following the shape of the data agrees well with a straight line. And so it's nice to have a simple model of a straight line rather than something more complicated. Okay? If you see really big departures between the low S smoother and the linear model smoother, then that suggests that maybe the straight line relationship isn't supported. Okay? And we could add a title on here. I'll just say model 1, because we're going to have 2 models in this data set. So we got a little title up there. Okay, did we get everything? If you knew a country's expression control or its score out of 10, with 0 being the most. Okay, so 0 is the most as you go, so the best place to be is over here to the left, I guess. And as you go to the right, you have more expression control. Does that mean that the person has control or that the government is controlling your expression? This question, is poorly documented here. Okay, political pressures and controls on media content. Okay, would you be comfortable using a linear model to break the personal freedom score? Well, we've got a straight line here, for sure. If the relationship looks linear, quantify the strength of the relationship with the correlation coefficient. So correlation is a measure of linear association. Okay, there's a couple ways to do this. The core function. Let's look at question mark core. Calculates the correlation, and you just need an x and a y. You can't specify a data set in here, so you've got to get the data in somehow. And then there's different types of correlation. We're here looking at Pearson correlation. The Spearman correlation is based on ranks when your data are not linearly related, and I don't remember what Kendall is. All right, when you have missing values, the word use can be included here to for special cases. Okay, so let's do the simplest thing. Right, one way to specify one way to get at variables is with the dollar sign. So if you've got HFI, the data set dollar sign, the variable name, it will print out the list of numbers. Okay, so we can get each set of list of numbers in that way, and we can just tuck those inside the correlation function for the x and the y variables. That matches up with the correlation of x comma y. Okay, so if we run this, we'll get a number. Another way to do that, if you're really trying to do everything through the tidyverse, which is not really possible. You can't do everything in the tidyverse, but lots of things you can do there. Usually, most things you do through the tidyverse makes things simpler, but there are scenarios where it is harder. So, for example, here's an example. You can take the data set, pass that into summarize. Summarize is a function that creates a single row summary for each group of data that you're passing it. So we're passing here one group of data. It is going to find the variables that we've specified in the data set. It's going to calculate the function of that variable, and it's going to assign that to a variable name, and it will return that as a single row. So here is a new tibble with core as one of the rows. Just to see a little bit more how summarize works, if you want to do like the mean of, yeah, I'm trying to not use a lot of characters, but anyway, here's a mean of the score. Okay, you can see, so you can ask for a bunch of summaries on the same group of data just by adding more and more of these summary commands. Okay, well, we've answered the question. 0.84 is a quite high correlation, in my opinion. Okay, so I think we've answered all the questions there. All right, question 4, Model 1 residuals. Looking at your plot from the previous exercise, describe the relationship between these two variables. Well, they are positively correlated because they have an upward slope. Correlation is a decent way to summarize the relationship because the relationship is linear. It's sort of a straight line relationship. It spans almost the entire range of expression control from 0 to 10. Sort of impressive. Make sure you discuss the form, direction, and strength of the relationship. Okay, so no code to write. Just answer the question. So, I could say something about answering questions. Right, I have posed the questions as 1, 2, as numeric. So instead of these stars, which create bullet points, you could do an enumerated list, right? So answer 1, and then 2, answer 2, right? So you could enumerate your answer as well, and take away the stuff that you don't need as you go. All right, model 1. At least squares line, building intuition. Okay, so this is a pretty cool app. If you run this line, you'll get in the plots window an app that it says click 2 points to make a line. All right, so where do we think this regression line should be? So we've already given ourselves a pretty good answer about this, but with that regression line, you can see I've specified to show the least squares, or show the squares, right? We're trying to minimize the squared errors. Each observation here is some distance from the regression line, and so it's taking that distance as the side of a square, and we have the area of the square now that we're adding up all the squares, right, the sum of the squares. And we're trying to find the line that minimizes the sum of the squared errors. And so with this line, we have a sum of squares, which is 111. And it has this intercept and this slope as the two variables that define the line, sort of like y equals mx plus b, the equation of a line, where b is the intercept and mx, m is the slope with x. Let's see if we can get better than 111. Okay. If I'm going to get better, it's going to be just by chance because I'm going to see the same thing. Ooh, 108. Okay, about every time. So, very good. All right, using this plot, run the function several times. You don't have any neighbors. If you want to go next door, ask them for a cup of sugar and see what their regression line looks like, you can do that. Otherwise, there are no points associated with this. Just sort of do it a few times and develop some intuition. What would a terrible line look like? Well, maybe something like this. Okay. Now, there's sum of squares is 400, whereas before I had 100. Right. We have these huge squares out at the left and right sides. So that is not a good regression line. All right, let's talk about the linear relationship in this model. We're actually going to fit a slightly different model. This assignment has a little twist to look at a slightly different variable because they go through on their introduction, and I recommend that you read this. It talks about the residuals as being the difference between the observed y and the predicted values that are the predicted values of the line. Okay, so if you take any single point here, like this point down here, its observed point is where the point is. That's where the data are, or this data point is. And the predicted value is, if you follow that x value up to the line, that's what's being predicted by this model. That's y hat. And that difference is the error, and that error is the length of this blue line. All right. The website goes through looking at the relationship between PF score and PF expression, and it talks through fitting the model using the linear model function. Tidy gives you some output. We'll take a look at that. And Glimpse gives you some other model statistics. So go ahead and read through that. But we're going to fit it now to PF and HF, which is the total human freedom score. All right. So we need to sort of mimic this example ourselves. We've got 1, 2, 3, and 4. Number 3 has write an equation, and I do have a couple equations written here that you can mimic. Okay. So plot the relationship. Well, we already have code to make a plot. Always copy. And we're looking at the human freedom score. So let's take a look at, and this is model 2. It pretty much looks the same, doesn't it? If we clear a couple plots here and go back, I want to click back and forth. So there's the model 1, that's model 2. So personal freedom, human freedom. They are almost the same in terms of like the linear relationship. So we're gonna get very similar results. All right, let's look at the questions. I can make this a little bit smaller. Okay, plot the relationship. Okay, fit the new model for this relationship. So we can copy the code from the website. We'll call this M2 as model 2. This is the human freedom, HF score. All right, and so in M2, there is the fitted object. Okay, if we just print it, it tells us what the linear model was that we used to fit the data, and it gives us the intercept and the slope. But there's a lot more that you can get. You can look at the summary of M2, and this is the traditional way of reviewing linear models. We have the quartiles of the residuals. Basically, this is to help us see if they're roughly symmetric. Our median should be close to 0. Our quartiles should be almost equally distributed on either side of 0. And ideally, our min and max are as well, though there's going to be a lot more variability for the most extreme points. But this looks very symmetric in terms of residuals. In the coefficients table, we have these estimates of the intercept, just like we had up here, and the slope. Okay. In addition to that, for the intercept and the slope, we have standard errors, t-statistics, and p-values. Later in the course, we'll learn about how to use these values here, but we're effectively testing the hypothesis that each of these coefficients equals 0 in the population. All right, we have some other statistics down at the bottom. The residual standard error is our estimate of the standard deviation of the residuals. We have the degrees of freedom, which is going to be the number of observations. So let's see, in our environment, we have 123, excuse me, we have 162 rows in our data set, okay? We had to estimate our intercept and our slope, which each took 1 degree of freedom. And so what is left over from the total numbers of degrees of freedom, 162, after estimating 2 parameters, is 160. And we have that many degrees of freedom to estimate the standard deviation or the variance of the residuals. We have some other statistics down here. The multiple R squared is the square of the correlation, but it tells us the proportion of variance that the model explains in our response over and above just a grand mean. Adjusted R squared is only used for model selection. Do not interpret it directly. Okay, and the F statistic is there to test whether all of our, the null hypothesis is that all of our estimates, not including the intercept, so just this value here, whether all of those, if you have got many x variables, are equal to 0 or not. So it's basically like the most basic model you could have, just the grand mean of the y variable. It has 1 degree of freedom in the numerator because we only have 1 x variable in our model. Okay, anyway, that's a whole bunch of stuff. There are more modern ways of looking at these results that come from the Broom package. So if we look at tidy, you'll see that this tidy part gives just the coefficients table here, which is pretty nice because it's a table, and if you were to fitting many models, you could work with these values as data. You probably want to add a column to label different models, and then you could print out the plot the estimates with standard errors and things like that. So it gives you a way to work with it. The other function is glance. So if we glance at this model, you can see this gives us some of the statistics that were here at the bottom, as well as ones that weren't. So we have R squared, adjusted R squared, and sigma. Those were all down here. Adjusted R squared, multiple R squared, and sigma. We have the F statistic here. We have its p-value over here. Degree of freedom is there. And then these were not part of the regular output. The log likelihood function, AIC and BIC are used for model selection, and so on. All right, let me get a little drink of water. Let's make sure we're answering questions. So we've got lots of output now. We plotted the relationship. We fit the model. Using the estimates from this model, write the equation. Okay, so let's choose one of these. I sort of like this first. The only difference between these two equations is that we have y as the first term as a response versus the actual variable name. I sort of like having the variable name more, so I'm going to delete this first equation, and we want to fill in these beta values, our estimates. So we have our intercept, and we have our slope. That's it. There are fancy ways of getting those numbers into the equation, and I'm going to skip it over that for this video. Okay, we wrote the equation. What does the slope tell us? Okay, so all right, for number 4, what does the slope tell us? We've got positive slope. Okay, the slope is that, which, so there's a positive increasing relationship as, the x variable increases as that increases, we expect the response variable to increase. Specifically, the interpretation of the slope for each unit increase in the x variable, we expect a slope value. We expect a 0.368 increase in the response variable. And for later on, I'll say holding all other variables or features constant. Okay. All right. So as you increase along the x-axis 1 unit at a time, the y variable is increasing by 0.368. Now it's a little bit hard to see with the default scale here, which is 0.25 units. Let's make a modification to our plot. This isn't really that important, but I think it's important for you to know how to do this. There are these scale X or scale Y or scale fill, scale color. You can adjust the scale of any attribute. And here we're adjusting the x-axis, and this has a continuous axis. Let's look at the help for this. We've got breaks and minor breaks. The major breaks are the ones that are labeled. So we want to set the breaks to, how about every 2? So that one way to get every 2 is a sequence from 0 to 10 by 2. So you can see I've got every 2 numbers here, right? So a sequence is a function from a lower bound to an upper bound by some amount. You can also specify how many values you want, the length. But often I think by is the nice way of doing that. So I've got the sequence, those are going to be my breaks. Let's do that. And you'll see now I've got 0, 2, 4, 8, and it would be 10 if it went up that high. The other thing you might want to use this for is to adjust your limits. There's multiple ways of adjusting limits. We know that the limits of this scale go from 0 to 10, so it might be nice to see it go all the way up to 10, and then you can be a little bit relieved that there aren't, values 9.5 up to 10. Maybe this doesn't include North Korea. All right. So I think we've addressed everything in that problem. Question 7. Model 1 prediction. All right, if someone saw the least squares line and not the actual data, how would they predict a country's personal freedom score? Okay, so we're back actually to the first model. So you can see I've put some code here for this first model. Let's go up and run the code for the first model again. You know what? I like the this x-axis. Let's take the code for this x-axis and put it up there as well. So model 1, I'm going to include that x-axis code. All right. That way we're looking at the data that we are thinking about in this model. Question 7. If someone saw least squares regression line, okay, we're looking at it, and not the actual data, how would they predict a country's personal freedom score for one with a rating, with a 3 rating? Okay, so a 3 rating is this line here where there's a 3. We go up right there. In fact, sure, let's just copy this code down here. We can play with the code. That way I can show you a little bit more stuff. All right. There's something called, you can make vertical, so geom, when you're doing ggplots, the objects that you're creating to plot are geometric objects. That's a geom. So there's a geom, there's tons of geoms. V line is a vertical line. If we look at the help for that, we can specify, there's geom AB line, which is AB is like A is the intercept, B is the slope. There's geom H line for a horizontal line, and there's geom vertical line, which has an x-intercept. That's what I'm looking for. So I want to make a, okay, so I'm just going to copy some piece of code here to get me started. So geom V line, and we can do x-intercept equals, and we can choose a number 3, because that is what the question is talking about. And we can do line type equals, how about dotted? Okay. So we'll run all this. And now we've got a dotted line. It's a little bit small in the video, I guess. Line size, I think. That will make it way too big. Oh, it's not that. Well, I know that there used to be size, but then they stopped wanting us to use that. Oh, here we go. Size aesthetic is deprecated. Use line width. Okay, line width equals 2. Okay, well, you can definitely see that dotted line, right? It actually is sort of annoying. The dotted line is a bad choice here. Let's do, we'll just do solid, which is the default. And we'll make alpha equals 1/2. Okay, I'm just trying to make a little reference line. There we go. If someone saw the least squares line, how would you predict personal freedom? Well, you would look at where it crosses the regression line. So where there's a 3, you go up to the regression line. That is just short of 6. So maybe it's like 5.9, something like that. I will show you a few other ways to do that. Is this an overestimate or an underestimate, and by how much? In other words, what is the residual for this prediction? So you have to look very closely to this plot. Let's see, if I click zoom, I think it creates a new window. We can make this big. And you can see that there's one observation here that had an exact 3 for the expression control. So that value is closer to 5.5. So it looks like our prediction was an overestimate of what we actually observed. Okay. And by how much? Oh, it's about 1/2 of a unit. Okay. But the residual is actually the other direction, right? It's what's the observed minus the prediction. Yes, it's negative. Observed is like 4.5. Oh, I'm already forgetting. Sorry, 5.5. The observed is 5.5 minus the prediction, which is almost 6. So we have a negative residual. All right, in fact, we can calculate it directly. Let's do that. So we're going to fit this linear model. There's the slope and the intercept. That for almost every model out there, you can make predictions from the model. So let's take, this is a little bit advanced. In fact, I'm just going to copy a piece of code from before. So I'm going to predict based on this M1 model. And I think if you just do predict, it will give you, yes, it will give you predictions of all of the observations. Okay, and we just want to make a prediction where this variable PF expression control equals 3. So you can also specify new data equals just that, a new data frame with just that variable equal to a single value, and this is our prediction, 5.9. That's roughly what we said it was, right? We can look at the data set where this is true. So if we start with the data set and we filter where expression control double equals 3, if we do just that much, we'll get the entire row. So this is for place in Africa, and its PF score is 5.47. Okay. This additional piece of code over here, pull, is a way of pulling out just a single column from a subset and printing those numbers. So in this case, this single number PF score is right here. So we've got the predicted value of 5.9. We have the observed value of 5.46. Okay. And you can calculate the difference of that if you wanted to. Sure, let's do that. No, it doesn't matter. You know how to subtract. Very good. All right, let's look at some model diagnostics. So, if a model is to be reliable or believable, we need to check the model assumptions. Most of them are here. So, we want linearity, that is the mean of the model, needs to be correct. We need our residuals to be roughly normally distributed. That's the spread vertically about the regression line. And that we have constant variability across the range of the data. And as you look at this, you might actually see constant variability. It looks like there's a bit more spread down here at the bottom and less spread up here at the top. I guess as you constrain people's expression, you actually constrain the variability around how much expression that they actually produce. Makes sense. All right, so I have a note here in the output. That's a place where it would be easier to read it. All right, so I have a function I wrote ages ago that you just pass into it. So it's called plot linear model diagnostics. You pass into it the model name, and that's it. And it prints tons of diagnostics. Now I have some switches to indicate which plot set you want, and for now the simple set gives us more than we need. We want to, and I'll show you how to interpret each of these. Okay, so I'm going to talk about all this, but you can read it also. All right, so we've got a plot here. Let me just produce it. Okay, by default, it's going to make grids of 3 columns in one row, so you can sort of scroll through the plots. Okay, this first plot here, the QQ plot, is a quantile versus quantile plot. It is the quantiles of our residuals. So if you arrange our residuals from lowest to largest, and you match them up with the quantiles of a normal distribution in terms of how spread out they are, if they follow this blue line, that means that the shape of our residuals is very close to the shape of the normal distribution. In fact, why don't we make just a little histogram of these residuals? So hist is a function for making a histogram, and if we look at the function residuals of a model, it will print out those numbers, the actual distances. So we can do a histogram of the residuals of M1. That's the simple way of doing that. Okay, so then you can ask, does this look like a normal distribution or not? You might change up how many bins there are, and at some point you'll have too many bins. Okay, 30 looks pretty good. Even the default looks pretty good. Roughly the shape is symmetric, but there's a little bit of a tail on the left. Okay, so that's the shape of the residuals. Does that match up with the normal quantiles? It basically does, except maybe right here at the left tail where we have these 3 values that are a bit more extreme than you'd expect. Maybe a 4th value right here. Cook's distance we're going to skip for now, but it talks about how influential each point is on the model. How if you add a point to the model, does it change the slope of the regression line or not? Cook's distance versus leverage asks whether that influence of Cook's distance is related to leverage. Leverage is how much of an outlier a value is in the x direction. So if you have an outlier for your x variable, is that influencing the regression model? We're also going to skip this plot on the right, this Cox power transformation. That's about if your residuals are not normal, what transformation could you suggest for the y variable to make them closer to normal? These plots are ones we're looking at. So residuals versus fitted, these are discussed in the on the Open Intro Stat website. Okay, model diagnostics. They talk about the fitted values versus the residuals. Okay, so here's the fitted values versus residuals plot. We have basically this red line is helping to guide your eye to any patterns here. I totally ignore it every time because it tends to have much more wiggle than is really supported by the data. So I see this as being fairly structureless in terms of the residuals, meaning there isn't like a curved relationship around the horizontal line. The zero line here is, you can think of it as being the regression line itself. That's where the regression line is, and the points are above and below in this pattern relative to the regression line of 0. But we do see this difference in spread, right? There's less spread on the right and more spread on the left, right? There's a big gap of open space in the bottom right and the top right quadrants. On the right here we have a very similar plot. It's relative to the x variable. In fact, these two plots are identical because there's a one-to-one relationship between the x variable and the fitted values, which is the y variable regression line. But I find it often easier to think about the residuals in terms of the x variable. So, all right, so pretty good except for maybe constant variance. Let's make sure we've so linearity, yeah, looks great. There's no like curvature suggested in this plot. Residuals and histogram, normality, yeah, I think the data are basically normal except for a few outliers on the left. And that's what I would say. Like these 2 or 3 outliers out here really are not influencing the model very much. There's more diagnostics we could look at to give us a sense of that. You know, it's actually these 3 points right here, 1, 2, 3. Those are having the most influence because in the regression model, I think it might be these 3 points down here have the largest negative residuals. Those 3 are also near the left end of this regression line, and so they're grabbing the regression line and they're pulling it down, right? They have a lot of leverage, just like on a teeter-totter, right? They're pulling it down. If you pull down in the middle, you pull the whole line up and down. If you pull down on the end, you actually change the slope. So that's what's happening, and that's why these 3 are the most influential. But I'm not sure it's affecting our actual inference of this relationship by very much. So I feel pretty satisfied leaving those points in there. Okay, and then constant variability, we discussed that as well. That this pattern seems to look like there's more variability for low expression control and less as you increase expression control. Great, that's the assignment. Let's make sure that what we've done renders. I did not provide a very good model of actually working on code as we go. It's probably nice to render it, maybe every problem that you have written, so that you know that you always have something that's working. If we refresh our results, maybe the only thing to really look at here is we've got our plots. I want to look at our equation. Here's our equation with our numbers. Looks very nice. The hat means it's a predicted value. Okay. We could also put hats over our numbers. People often don't because they are by virtue of them being a number, they are an estimate, whereas when they were a symbol before, it may not be obvious, so you put a hat over it to know that you're going to estimate it with data. All right, the rest of this looks pretty nice. There's our vertical line and our residual plots. I like their display when they're nice square boxes. To get square boxes, by the way, if you set the figure width to 8 inches and figure height to about 3 inches, that gives you a pretty nice display of these plots. Okay, very nice. Well, I hope that was very helpful for you to get started and completed with this assignment, and I'll see you in the next one.